Hello everybody, my name is Ping Li from Southeast University in China. The authors I work with are Ming Chen, Yijie Mao, Zhaohui Yang, Bruno Clarks, and Mohammed Sheikh Bahai. The topic of my presentation is Cooperative Rate-Splitting for Secrecy Rate Enhancement in Multi-Antenna Broadcast Channels. I'd like to divide my presentation into 4 parts. Firstly, I would like to introduce the motivation of our research. Cooperative rate splitting is designed based on rate splitting multiple access, which is a promising multiple access technique that outperforms conventional space division multiple access and non-orthogonal multiple access. Due to the broadcast characteristics of wireless communication, data transmission between devices is easily exposed to eavesdroppers, which poses a challenge to secure transmission. Existing physical layer security transmission technologies mainly include beamforming technology and artificial noise design. In particular, the generation of artificial noise needs to spare part of the transmit power to ensure secure transmission. And most of the existing works on physical layer security are based on multi-user linear precoding and NORMA. Secondly, I'd like to introduce the system model and problem formulation in our paper. From the picture, we can see the system consists of a base station with multi-transmit antennas, 2 single antenna legitimate users, and a potential single antenna eavesdropper. In our paper, we assume that U1 experiences a better channel than U2. The superposed transmit signal is described in equation 1. Consider half-duplex model, which is shown in figure 2. Theta is the fraction of time assigned to the direct transmissions. The respective receive signal at UK and E in direct transmission phase is described in equation 2 and 3, where the superscript 1 represents the direct transmission phase. The signal-to-interference plus noise ratio of decoding the common message at both users are described in equation 4. In the cooperative transmission phase, the respective receive signal at UK and E are expressed in equation 5 and 6. Thus, we can compute the SINR of decoding the re-encoded common message at U2, which is shown in equation 7. Easily, we can know the corresponding achievable rate. The legitimate users decode the private message individually after removing the common part, where successive interference cancellation. As the precoder of the common stream designed at the base station only ensures the decodability of the common stream at the 2 legitimate users, the eavesdropper may not be able to decode the common message. Hence, the common message can be treated as artificial noise at the eavesdropper. To meet this requirement, the condition 13 should be satisfied. Following the similar format, the receiving SINR of decoding the common message at each phase and the private stream at the eavesdropper is described in equation 14, 15, and 16. Then it is easy for us to write the corresponding achievable rate. In our paper, we add up the three parts: the achievable rate of common message and the private messages for both users, and call it achievable secrecy sum rate. In this work, we aim to optimize the precoding and time slot allocation with the objective of maximizing the SSR subject to transmit power constraint. Mathematically, the SSR optimization problem is written as equation 20. Okay, now we move to the third part, optimization solution. Before solving the optimization problem, we first analyze its convexity. The max operator is convex, while the double max is non-convex. Furthermore, the elements in max functions are neither convex nor concave. To simplify the original optimization problem, we first decompose the optimization problem to draw the elements out of the max operators. Then we perform a series of linearization to deal with its non-convexity. As the non-convexity among all cases are similar, we next specify the optimization framework to solve case 1 for simplicity. To handle the non-convex problem case 1, we need to introduce some auxiliary variable vectors. According to the sequential convex approximation algorithm, we can solve the original optimization problem by computing the subproblem shown in this slide, and these are some related equivalent expressions. Now we come to the last part, numerical result and conclusion. In both sub-figures, the proposed CRS performs better than MULP and cooperative norma, which is due to the fact that the proposed CRS uses the common message not only to serve as artificial noise for impairing the decoding of the eavesdropper, but also to enhance the interference management among U1 and U2. When variance of the link from base station to U1 equals 1, while variance of the link from base station to U2 equals 0.3. The average SSR gap between C norma and CRS decreases compared to both the variance equal 1. It shows that C norma is more suitable to the scenarios where the users experience a larger disparity in channel stresses, though C norma performs generally quite poorly compared to other schemes due to its inefficient use of multi-antenna. In a word, CRS is a promising strategy to improve the physical security in multi-antenna broadcast channels. Thank you.